It is our honor to have Professor Kenneth Young to give us an introduction on the Shaw Prize. May I invite Professor Young, please?
Good afternoon, ladies and gentlemen. Thank you for coming to this public forum organized by the Leisure and Cultural Services Department, the Science Museum, in collaboration with the Shaw Prize Council, in order to provide an opportunity for members of the public to meet, to listen to, and to interact with the Shaw Laureates 2017. The Shaw Prize was established in the year 2002 to promote and foster scientific research worldwide. It is an international award dedicated to honoring individuals, regardless of race, nationality, gender, and religious belief, who have achieved significant breakthroughs in academic and scientific research or applications, and whose work has resulted in a positive and profound impact on mankind. Since 2004, the prize has been awarded annually for distinguished and significant achievements in the following three scientific disciplines: astronomy, life science and medicine, and mathematical sciences. Each prize consists of a medal, a certificate, and a monetary award of $1.2 million. This is the 14th year in which the prize is awarded. The 2017 prizes were awarded just 2 days ago, with the chief executive officiating. We are pleased and grateful that the laureates, in addition to lectures at 3 universities yesterday, are here today for this forum. I leave it for the moderators to introduce the laureates. I just want to say at the very outset how impressed I have been by their total dedication over decades in working on problems of importance to humanity. Important not only for the impact on our lives and our health, but also important as part of the rigorous and relentless search for truth and understanding that distinguishes us from other species and defines us as humans. While the Shaw Prize celebrates great achievements of the recent past, it is also intended to promote similar, dare I say, even greater efforts and achievements in the future. The science of tomorrow belongs to young people, and we are very pleased to see so many future scientists here today. I'm sure you will all be captivated, as I certainly shall be. Thank you.
Thank you, Professor Young. Now, let us begin with the sections on astronomy. Today, we are much honored to have Professor Meng-Chong Zhu to be our moderator. May I invite Professor Zhu, please?
Good afternoon. It's my great honor and pleasure to introduce the Shaw Laureate in Astronomy 2017, Professor Simon White. I see many young audience. I don't know how many of you have had the experience of watching the stars in a dark and clear night. It's getting more and more difficult in Hong Kong now. I myself have been doing it since 40 years ago, when I was in junior high school. And I still remember that whenever I looked at the skies and the Milky Way and so on, I would be wondering, how would the universe evolve to be like this? This must be one of the greatest questions in science. And Professor Simon White has done seminal work to providing a framework of the answer for us, how structures evolved in our universe. More importantly, he has shown by doing his research, he has shown by example, that we could study these very important, very fundamental questions with the help of powerful computer. So now we can actually simulate the evolution of the universe. We can change the physics, we can change the particles, we can change many things. We make our own universe. It makes it almost like a lot of fun that you can play around with the universe. So now, these sort of simulations, sometimes you call them n-body simulations, become a very standard and powerful tools in cosmology. Professor White has also done a very beautiful and surprising work. He showed us that such simulations can tell us not just about the macroscopic universe, but even about some properties of elementary particles. It turns out that neutrinos, which is very abundant, and we now know that they have some finite non-zero mass. Turns out that neutrinos have a great impact on how structures evolve. And because of this sensitivity, Professor White could produce a very tight band on the neutrino mass, much tighter than what people can measure in the lab. So by studying the universe, we know something about the tiniest particles that drive our universe. So this is just an example of the beautiful work Professor White has done. So it's my great honor to invite Professor White to give his talk.
Good afternoon, everybody. It's a great pleasure to be here. So I started thinking about problems in astronomy and doing astronomy about 40 years ago, which is a very long time for most of the people in this audience. At that time, this was the biggest telescope in the world. It has a main mirror 5 meters across, and it sits on a mountain called Mount Palomar, south of Los Angeles. At that time, in the mid-1970s, it was already 20 years old. And even today, 40 years later, it still does forefront science. So this main instrument has lasted 60 years. Now, at the same time, I was using computers for my research, and this was the biggest computer I had access to. It was made by IBM. It was called an IBM 370, and there was one in Cambridge University. It was 2 years old when I started using it, and it was scrapped and thrown away 2 years later. Computers change much faster than telescopes. And in fact, since I started, computers have become 1 billion times more powerful than they were. And they can handle 1 billion times larger memory. They have 1 billion times more information. So this is a huge expansion compared to most other capabilities in our science. When I started, we programmed computers using punch cards, and you had to sit down and type on these little machines, and they punched the instructions on cards, and then eventually you'd get a whole deck of cards. You'd have to, the deck of cards would be in a big box, and in my case, I didn't even have somewhere to read it in the department where I was working, so I had to take the box of cards, put it in the basket of my bicycle, cycle through the rain across the road to where there was a reader which you could put them in, and it would read the cards in, do the computation, and eventually you get the output back, and you get it in the form of print on a large stack of paper. It was a printer called a line printer, which printed 130 characters or so at a time, and we go, and eventually you get the printout. And that was all you got. There was no graphic printers, no way to make a picture. So that was a problem. The problem I was interested in goes back even further. So this is a picture of a cluster of galaxies, and all the white, light-colored blobs that you see here, these are elliptical galaxies. You can see there are many of them in this region. It's what's called a galaxy cluster. And by measuring the size of this region and how fast these galaxies are moving, you can estimate how much total mass, how much material is in this region. And this was first done in the 1930s by this man. This is much later in life. He was a Swiss astronomer called Fritz Zwicky. He did this calculation, and he got a strange answer. He found that the total amount of material in this region seemed to be more than 100 times the mass of all the stars. So apparently, most of the material in here is in some form we can't see. And this became known as the dark matter problem. And then that sat there for more than 50 years without a solution. Some people thought the problem was actually the laws of gravity were different for these big systems, or there's just a lot of stuff we can't see. So this interested me when I was a student, and I wanted to calculate what would happen if this extra matter was somehow attached to these galaxies just in the outsides and it wasn't shining. So to answer that question, I needed to ask, how would the system change with time? How would it evolve if this were the case? And there are about a few hundred galaxies in here, so I tried to calculate this. And luckily, this man, who is a Norwegian astronomer who was working where I was working, had all written a code which could calculate how stars would move inside a star cluster under the influence of their own mutual gravity. So I just took his code and reprogrammed it to follow what would happen with galaxies inside a galaxy cluster. And here they are distributed uniformly and expanding with the universe at this time. And I just asked what would happen as this system evolved. And a bit later, it got about 5 times bigger. So this bar is actually the same physical size here and here, and the whole system's expanded. And you see it broke up into lots of lumps. And then, a bit later, these lumps coalesced into 2 big lumps. And then finally, it all fell into one single lump. So apparently, the way the structure evolved was starting smooth and getting gradually more and more lumpy until you end up with a single system. So there's several things to think about here. I didn't know what was going to happen when I started this calculation. So in some sense, this is an experiment. But it's clearly not an experiment on the real universe. It's an experiment on this set of mathematical equations, which just enforces Newton's law of gravity between all these particles. And so I couldn't calculate directly on a piece of paper how this would happen, but the computer did it for me. So it's a kind of computer experiment on the mathematical model. So then an interesting question is, does this have any correspondence with reality? And I was quite lucky that a couple of years later, this X-ray telescope flew. It was the first, it's on a satellite, and it was the first telescope which could take pictures of the sky at X-ray wavelengths. It took pictures of galaxy clusters, and it found some that looked like this, some that looked like this, and some that looked like this. So then it's very tempting to say, well, this is just kind of an evolutionary sequence. This is the early stage, this is an intermediate stage, then eventually it all collapses. So maybe somehow doing the computer experiment is helping us understand something about how the complex systems might evolve in the real universe. So that was 1976. So you can ask 30 years later, what happens if we try and do the same experiment? So as I told you, computer power has been increasing dramatically. So now instead of having just a few hundred at points in the simulation, we have 100 million. And we have to calculate the forces they all have on each other. You'll see with time it starts out very smooth, and as time gradually changes, small lumps form, and you start to see a pattern emerging with small clumps. And then you can see these clumps. It looks as though it's rotating, but you have to imagine that the observer is just flying around the system. This is to help you see the three-dimensional structure of the object. It's not really rotating. And you can see now a really complicated structure has emerged. And all this structure is eventually going to fall together to make one single system, which is supposed to represent the dark matter part of a galaxy like our own Milky Way. You can see now there are many, many lumps here, and these ones in the central region will start to coalesce, and you'll see a little later how a single system starts to emerge. So you look at this, it would be very hard to try and predict all this complexity just from the equations. You need the computer to try and understand how the interaction between all these different equations, all these different bodies, all these different lumps, how this nonlinear pattern evolves. And so this is, in a sense, is what we mean by a computer experiment. And what I find fascinating is you look at this kind of thing, you don't really know when you start what it's going to look like. And you can see here, actually, the person who made this movie made some parts green and some parts blue just to make it even prettier, but that doesn't really have any significance. But now you can see we're getting close time. There's a clear center to this system. There's a clear drop-off in the density of dark matter as you go away, and there are all these other bits of stuff flying around. So you get a very complicated structure. So the difference between this calculation and the first one I showed you is just 30 years of computing. Treat a much more bigger system, so you see much more complexity. But the basic conclusion is the same. You start smooth, you get lumps, and the lumps coalesce to make larger and more coherent structures. So for the next part, which I want to talk about the evolution of the universe as a whole, I want to show you this picture. So this is a modern picture. It's a picture of the sky taken by a European satellite called Planck. It's taken in light with a wavelength of 1 millimeter. So that's about the same wavelength as the microwaves in a microwave oven. And what you're seeing here is what's called the cosmic microwave background. And this is a map of the whole sky. And you can see there's a kind of pattern here. What you're seeing, I think, makes this one of the most remarkable pictures in all of science, because this is a direct image of our universe as a whole when it was only 400,000 years old. So today, it's 13.7 billion years old. But at the time we see, it was 400,000 years old. And in fact, this map is very nearly smooth. The intensity here is measured by a temperature, and the average temperature here is 2.7 degrees above absolute zero. And the difference between the red points and the blue points, between the peaks and the troughs, is only about 1 part in 10,000. So it's very nearly uniform, and just very small regions which are higher and lower. So back in 1980, when I was first thinking about this problem, the map at that time looked like this. We couldn't measure the differences, but we did know it was very smooth. And so the question is, it was very smooth when it was 400,000 years old, and it's very lumpy today. How do we make the transition? And it became clear from relatively simple arguments that if the whole universe was this smooth and nothing was lumpier than the limits you could see, there wasn't enough time to make anything. The universe would still be smooth today, which obviously it's not. So the hypothesis was we needed something back then, when the universe was very young, which was smooth and didn't interact with the light and the ordinary matter, because then it could be lumpy and you wouldn't see it in the light. So we need dark matter even then. So the question is, what could this stuff be if it doesn't interact with light? So one possibility, in fact the only possibility which we know to exist, is that it could be a neutrino, which interact very weakly with ordinary light, and those neutrinos had mass. And at the time, no one knew whether neutrinos had mass or not. So we tried to say, if neutrinos had mass, let's do an experiment and ask what would the universe look like. And when we did this, we found that the galaxy distributions should look like these pictures, whereas this is the galaxy distribution measured on the sky in the real universe. And you can see the structure doesn't correspond. The lumps here are much bigger, and the empty spaces are much bigger. So even if it was a computer experiment, we could exclude the possibility that that the dark matter was any known kind of matter, because neutrinos were the only possibility, and they didn't work. So it had to be something new. And then we showed if you took a new kind of matter, you could get it to work. You can see these look much more similar. And even if you look in the third dimension, we're now at the center, and this is looking away from us in distance. This is a slice of the real universe. These are slices of the simulations. You can see qualitatively they're similar. So this was the beginning of what's known as the cold dark matter universe. And this was me at the time. See, my hair is darker and shorter. These are my colleagues. So you can ask, that's what happens with 30 years of computers. This is what happens with 30 years for people. So you can see they dress better, their hair is shorter, but it's grayer. But that's the way life goes. Computers nowadays look like this. This is another younger of my collaborators who's great at programming complicated equations and making them work on very big computers like this one. This is just one row. There are several rows of cabinets like this for this computer. And they allow you to do simulations for how the structure grows. So here now we're looking at the structure growth in a larger region of the universe, and you can see the material gradually falling together to make an object in the center. So what happens with time is the contrast grows, structures become there, and you make the individual objects. So you do this with a large number of particles, in this case 10 billion particles, so 10 to the 10 particles in this particular simulation to represent the distribution. You get a very complicated structure. You want to see it in detail, it's best to take a spaceship and fly through it. So this is now flying through this virtual universe inside the computer. And that has a big advantage that in a virtual universe you can fly very fast. So this is 10 to the 14, so that's 1,000,000 billion times the speed of light. So that's pretty fast. You cross the whole universe in about 3 minutes. And you can see you find a very complex structure. The disadvantage is this is the dark matter, and we can't see it. So you have to somehow model the part that we do see so you can make the transition from the dark matter to the light. And now, if you put a virtual observer inside the computer, you can look at the galaxy distributions. So these are distributions of galaxies, so that we're at the center in each of these plots, and there's a distribution of galaxies in a slice of the universe. So these are real slices, these are slices inside the computer, and you can see qualitatively there's actually quite a close fit between the statistical properties in the two cases. And so by adjusting this, you can understand exactly what physical processes need to take place to get the match to be as exact as possible. So I think what you can see is this kind of work adds to the classical idea that we go to scientific truth by combining experiment or observation of the real world with a mathematical model for the processes which control things. And the problem is, for many processes, like the ones I've been showing you, but also like climate or economics, the systems are so complex that even though if the mathematical model is simple, we can't work out its consequences. And so the computer simulation allows you to do experimentation on the mathematical model, and then so to compare it with the observations. So we now have these three aspects which work together to try and improve our physical understanding. So I'm going to stop there.
Thank you very much, Professor White. Please take a seat here on the stage. The question and answer section is about to begin. May I also invite Professor Zhu to take a seat on the stage to join the discussion.
So, Professor White, thank you for such a stimulating talk. The floor is now open for questions.
Thank you, Professor, for your very interesting talk. I'm a biology student, so sorry if it's a very naive question. I would like to ask about the Newtonian n-body problem. Whether each dot has its own mass, and if they interact, if they have its own mass, will it affect how the model will form? Thank you.
I'm not sure I understood your question. You're asking about the correspondence between the things that we put in the simulation and the real particles, or what are you asking?
All the dots are uniform, but are they the same, or each particle?
Yeah, in the simulations I've showed you. So, for example, in the movie which I showed you a fly-through to try and understand the structure, that followed 10 to the 10 individual particles, which are all of the same mass, but they're still much, much more massive by about 60 orders of magnitude than the individual elementary particles. So you have to think of them as just a random sampling, a Monte Carlo sampling of the true particles. And so, of course, an important question is whether this very coarse representation of the true distribution is good enough to get the structure right, and that you'll have to do careful testing through more numerical experimentation to see if that was enough particles. And the answer you find is it's enough particles for some things and not for others. So you have to be careful when you look at the results to understand which parts of the pattern that emerges are independent of the fact that we had 10 to the 10 and not 10 to the 20, and which parts that's important for.
Thank you very much for your explanation.
I guess you can do an experiment with the computer, which we can't do in the real world, which is to make the Big Bang happen again and again. So if you do that, what is the variation in the structure through the simulation? In other words, like how, you know, if you run the simulation from the beginning, there must be, you know, a great deal of...
Well, that's true. And so I showed you the picture where you were supposed to compare the blue points, which were the real world, with the red points, which were the observation. And you can see that the patterns were qualitatively similar, but the lumps were not in the same place. So the goal is to make the pattern be statistically equivalent, but not to actually simulate the particular realization of the initial conditions we have. So if you run another simulation with all the same assumptions and all you do is change the random number generator in the initial conditions, then you get something where the statistical properties of the distribution are the same, but all the lumps and the voids and the filaments are in different places. So that's the kind of variation you get. And that's fairly easy to control for, because in any case we're trying to do a very large region of space, so different regions of space are almost independent realizations of the process anyway. But there's a more complicated aspect to what we're doing, is although we think we understand the physics at a microscopic level, you know, it's like we understand microscopic physics and chemistry on the Earth's surface that doesn't allow us to predict the weather. And that's because we can't treat things in the detail needed for the macroscopic system. And so, particularly where to put the galaxies, we have the same problem. We can't treat the physics at that level of detail. So actually we do experiments where we change the representation of the physical process and run it again and see if it comes out looking better. So this allows us to do effectively numerical experimentation on the proper representation of the physical processes. Because we have to have some kind of coarse-grained representation of how stars form and how black holes explode and so on.
So for your simulation, you assume initial starting conditions which are relatively uniform. How do you account for the quantum irregularities that arose as a result of the great inflation and would thus have affected the distribution of matter in the early universe?
Yeah, that's a very good question, because of course if we set up our initial conditions and they were completely uniform, by symmetry they could stay completely uniform and we wouldn't get anything. So although the initial conditions are nearly uniform, the deviations from uniformity are very important. And so we make the deviations from uniformity be consistent with the pattern I showed you in the microwave background radiation, because there we can measure directly the pattern of structure in the universe when it was 400,000 years old, when it was very, very smooth. And so what we do is we take that pattern, or at least a theoretical representation of it, and we use that to set the deviations from uniformity at the beginning of our simulation. And that pattern itself is consistent with what's expected if all the structure arose in the very, very early universe in the inflationary epoch. So because you can also start from the microwave background radiation. So what I showed you, this picture, is actually the boundary of the whole visible universe, because the universe in front of this cloud surface is transparent, so we can see it, but it's opaque, so we can't see anything, at least the electromagnetic radiation, that's behind it, so at an earlier time. But we can try and infer what could have happened at an earlier time to produce this pattern, and the simplest models for quantum fluctuations in the very early universe produce a pattern which statistically are consistent with what's seen. So this, you can take this microwave background pattern both as a starting condition for what I do, which is what happens in the late universe, but also as a way to test these theories of what happened in the very early universe.
Okay, the next question comes from the floor. So in case you're too shy, you're welcome to write on a piece of paper. Either English or Chinese will be fine. I will translate it for you. So I'll simplify this question. Basically, it is about the neutrinos. Is it the gravity of the neutrinos that affects the structures? How can such a low mass particle change the structures of the universe?
That's a very good question. So you can ask, why can we say that neutrinos are no good for the dark matter, but some other hypothetical particle called dark matter is great? And that comes from this question about what it predicts to come out of the early universe, so what it predicts for the initial conditions. And it turns out that neutrinos interact weakly with ordinary matter in earthbound experiments, but the interaction is not zero. And in the very early universe, the neutrinos were actually in interaction in equilibrium with all the other particles. And so that allows us to calculate when everything was nearly smooth, and we can calculate rigorously, formally by what's called using linear theory, it's possible to calculate in a simple way how the structure evolves. And it turns out that the structure in the neutrino distribution is smooth on very small scales. So the initial conditions in a neutrino universe are smooth on small scales, but still have structure on large scales. So that's why in the picture, when we evolved it, you found you got big lumps and no small structures. So the difference with the cold dark matter is the interactions were even weaker in the early universe, and the particles were more massive, and this means they had not only the big structure, but also smaller structures. And it's the smaller structures which you saw in the movies, making little things which gradually fell together to make bigger and bigger objects. And so that's the difference. It's the different kinds of particles give rise to different initial conditions in the early universe, and then we just put the conditions into our calculations and see what happens. And so in a sense, all these particles interact very, very weakly with light, with ordinary matter, but they interact in different ways, and those interactions actually do make a difference to what comes out of the Big Bang.
Thank you for your lecture. I have a question. How do you account for universe expansion during your simulation?
Well, we put it in. So it's essentially, it's initial condition. We start everything, you can think of it, we start all the material flying apart, and it just continues to do so. So in a sense, it's there as the way we set the calculation up.
Oh, I actually still have another question. We have an infinite universe, but when you put it in simulation, you have to consider a bounded physical system. Then how do you get rid of the boundary effect?
That's a very good question, although on the first point, we don't actually know that we have an infinite universe. Right? What we can see is definitely a finite universe, because all we can see is as far as this last scattering surface, and there's definitely a finite volume inside that. And the overall, whether the universe as a whole has finite volume, depends on its geometry in even larger scales. And we have some limits on that, but basically we don't know. So it could be infinite, and it could be finite. So this is an unresolved question. But in any case, it's much, much bigger than the simulations I'm showing you. See, our question's still a good one. And what we do in the simulations is we take a cubic region, and then we identify the top and the bottom and the left and the right and the front and the back, and make it periodic. So what happens then, it's effectively infinite, but it's periodic. And that allows us to avoid having any sharp edges.
Thank you for your answer.
Another question in the back?
Is there any special methods used in calculating such a complex structures you show to us, the evolution of it? I think, as I know, if I use a console software in the computer, it will take a lot of partial differential equations, and I will break down my computer.
Well, the whole point was the computers are getting bigger, but conceptually, I show you a simulation with 10 to the 10 particles. All that it did was, in effect, was to evaluate the Newtonian force, so G m1, m2 over r squared for every pair of particles. The complication, of course, is you have 10 to the 10 particles, you have 10 to the 20 pairs, so it's a lot of operations, so you have to find ways to speed things up. But conceptually, it's not complex. The complexity comes, if you like, from the initial conditions and the nonlinear development of the initial conditions, which leads to this geometric complexity. And that's a property, in a sense, of the initial conditions, which in one sense are very simple. They're the simplest possible stochastic initial condition, what's known as a Gaussian random field. But nevertheless, that evolves into a very complex structure.
Yes, but I still have a question. I want to know, how do you simplify the interaction between the particles or the matters? No simplification? No. The algorithm has to find ways to speed things up. But conceptually, what we're doing is really evaluating the forces between all pairs of particles and then just integrating the equations of motion.
Okay, if not, let me read the following question. How were you able to observe the dark matter when it cannot be seen with naked eyes? Also, how does the mass affect the expansion of the universe, and how can you simulate that?
Well, it turns out the dark matter, dark matter only interacts with ordinary matter and light gravitationally. So that means if you see it, you have to see it by its gravitational effects. So an example which you might well be familiar with is you can tell if you see a star which is just going round and round in circles, and there's nothing in the middle, that suggests there's a black hole in the middle. Right? So you can't see the black hole, but you can see the other star going around it. So what you're using is the gravitational effect of the black hole to see the star. So if there's a large lump of dark matter, that acts gravitationally on everything, in particular on the galaxies you can see. And so that's why Fritz Zwicky could tell there was dark matter in the Coma cluster, because he saw the galaxies were moving too fast. If you just took the gravity of the things you can see, they should be going slower. There's a way to be more precise about this, which is if you have a lump of dark matter here, and you look at a galaxy which is behind it, then as the light comes from the distant galaxy to you, it has to go through the cluster. And as it does that, the gravitational effect of the cluster bends the light rays, and that distorts the image. So it's like you look through a lens, and it's not a very good lens. Everything you see looks distorted. So we can see that effect. We can see the distortion of the galaxies in the background. By measuring how much their images have been distorted, we can work how much mass there has to be in the cluster. So this actually allows you to measure the mass distribution in the cluster by its effect on the light of distant things coming through it.
Is this an example of entropy when the universe went from order to disorder?
That's a very difficult question. The highest entropy system is thought to be one in thermal equilibrium. So that would be everything at the same temperature and uniform. And what I've been showing is you start with something which is uniform and hot and becomes cold and structured. So this does not look like entropy is increasing. It looks like things are becoming more. So it looks like entropy is decreasing. And this is it's actually a very deep question because it depends on how you assign entropy to the gravitational field itself, which is an unsolved question. So another example is if you take a cloud of gas, it can be relatively cool, but it can hold itself together if it's massive enough by its own gravity. What happens with time is it loses radiation, so it loses energy. What happens is then contracts, becomes more compact, and gets hotter. So the result of losing the energy, which you'd think would normally cause things to cool down, actually makes them get hotter. So a gravitational system like a star seems to have a negative specific heat. You take energy out and it gets hotter. And that's another effect of the gravitation. And so these kinds of effects make it very difficult to define exactly what you mean by entropy when you're dealing with gravitating systems.
Another question here. What is the uncertainty of the model?
Well, there are two aspects to the uncertainty. One is, there's a mathematical model, and the computer calculates the solution for a set of initial conditions. So in that sense, the experiment is a mathematical experiment. You're asking, have you got the right solution for this particular problem with this set of equations and these initial conditions? So then that's easy to handle because you can do tests and work out whether the computer has got a solution which is good enough. It's never going to be accurate in the sense a mathematician would like it to be accurate, but it can be close enough to make inferences about the structure. So that's relatively easy to do. You can test it by running the simulation with different integrators and so on. The more difficult question is, of course, the model that you put in is only an approximation to reality. And so that part, all our physical models are only some approximation to reality. And there, actually, the most important thing is when the model fails. Because when you're sure you've solved the equations correctly, and the answer still doesn't agree with what you observe, this means that the your mathematical representation of the physics is wrong, and you have to change it. So that's actually where we learn about the astrophysical part of the problem.
Okay, there's a question on this side.
Good afternoon, Professor. I would like to ask a question. There's a famous paragraph in the world that means that in the unseen galaxies, there is no aliens, because if there is any aliens live in other corners of the galaxies, they can see in any corner to the Earth in this maybe 4.6 billion years. Do you think is there any aliens live in the world or live in the galaxies or in other corners? Do you think so? Sorry.
I don't know. But I think one of the developments in astronomy in the last 20 years is we've come to understand that most stars, like the Sun, have planets, and very frequently they have planets which are like the Earth and have environments which are like that on Earth. So the kind of environment we have on our Earth happens millions or even billions of other places in our galaxy. So, and a lot of those systems are older than 4.6 billion years. So many of them have had more time to think about evolving life than has happened on Earth. So it would need something very special that we don't understand about the conditions on Earth for this to be the only place that's made life. On the other hand, the nearest planet that's made life could easily be much further than, say, 100 light years away, because compared to the size of our galaxy, 100 light years is not a very big region. So, if it's 100 light years away, then they won't know we're here yet, because basically we only became visible to the aliens once we switched on TV. And we started broadcasting TV. The radio waves are loud enough that any civilization which had a telescope as good as ours would know if it was within 70 or 80 light years of the Earth. And maybe they have, but it would take them more time to get back, so they haven't had time to come and visit us yet. But, I don't think there's any sign they've been here so far.
Well, actually, I always suspect that some of my students are aliens, so I think they are here already. It's a question from...
It's time.
Yeah, this one first.
What does your model show about the implications on the fate of the universe?
Sorry, about what?
The fate of the universe.
The fate?
Yeah.
I don't think this is really related to my model. My model follows the detailed evolution, so we could extrapolate further, of course. We don't have to stop the computers today. It would get very time-consuming. But I think we don't know. What we do know is that currently the expansion of our region of the universe is accelerating. So if that continues, then it'll get very cold and very uninteresting place in about roughly 100 billion years' time. All the stars will have died out, and most activity will cease, so it'll start to get really cold. And maybe things will never come back together. But on the other hand, outside the microwave background surface, it's possible that conditions change. And so we don't really know. That's an extrapolation. It assumes that the things we can't see look the same as the things we can. And this may or may not be the case.
And there's a question in the back.
Good afternoon, Professor. I'm a student from CUHK Shenzhen. And I want to ask that in your analysis of the simulation results, what method do you use? That it's very unlikely that only for the physicists to analyze those numerical results. Is it helpful for you to use that machine learning stuff or that something like that?
Well, it's true that you get very complicated patterns out of the simulations, and now the surveys of the universe have millions or tens of millions or even hundreds of millions of galaxies, so they have also very complicated structures. So it's possible that machine learning or some automatic routine would help find patterns that you don't see by other techniques. But at the moment, this hasn't played a very large role. There are many techniques which allow you to analyze the structure in a more directed way than just telling the computer to look at it and see what it thinks.
The time is almost up, so let me take the opportunity to ask the last question. So it's really this very simple-minded questions compared to the questions before. So what advice would you give to the young students in the audience aspiring to be cosmologists, scientists?
I think you should do what you find interesting and what you think you're good at, and you should worry about whether this is going to lead to a job later.
Okay, thank you. That's a good way to start.
Thank you very much. Please return to your seats on the floor.